Today we'll continue the discussion of the kind of how propellers work with starting at looking at Hartzell propellers. And just like McCulley, Hartzell's got two kind of versions. One is their steel hub propellers, or their older version. And then what they call their compact propellers are their newer version. They're newer, what you see on more modern aircraft. So the steel hub is shown here on the left. And there's a few features of these that you can point out. So it has an external pitch change mechanism. So this dome actually moves. Okay, so we're on the McCulley propellers. Sorry, on the McCulley propellers, and on the compact propeller, there's a piston inside the dome. In this case, the dome itself moves forward and back. And so there's external linkages that connect that back to the blades. And then you can also see sticking out at the base of the blades on each side this is a counterweight right here at the very cuff, at the very base of the blade. Okay. Versus the compact propeller where there's a piston inside of this small dome here, and there are no counterweights on the blades. So if we cut those away, they look something like this. Here is that dome. You can see it says there's this dome right here, okay? And there's a high pitch stop. What happens as this dome slides forward, it can only slide so far. You've got stops built into that mechanism. So you have a high pitch stop and then a low pitch stop that limit how far that dome can travel. And it's linked back through these rods right here, rods and linkages, to the base to the cuff of the propeller, the sliding rod. There's one on each side. And so that's going to perform that. So you can actually see this one, you can see the majority of the mechanism operating from the outside. When you take the spinner off, this is all exposed. There's no air charge here. When you look at them, there's no air valve on the end, typically. They call it a spider hub because of all these kind of linkages wrapping around it. And then the blades themselves, remember, have a counterweight. And so those counterweights are going to increase the angle, the blade angle. That centrifugal force is going to try to pull that counterweight in line with the plane of rotation and increase the blade angle. So then the oil, when we pump oil through this center shaft and fill this dome area in front of the dome itself is the piston. They call it the piston. When we fill this area under the dome, that's going to push this dome forward. That's what's going to drive to a low blade angle. And when we release, when the governor, I should say, I'm saying we, but we're really talking about the propeller governor here. So the propeller governor, when it ports oil to the dome, it's going to fill the area behind the dome in front of this piston and drive it forward or to the right. And that's going to pull it to a decreased blade angle. And then when the governor cuts off or removes pressure from that oil, it's able to flow out of the dome, back into the engine, because these counterweights are going to push the blades, are going to rotate the blades by going back to that plane of rotation. Okay. So that's the steel hub. And again, that tends to be an older design. What you see now is the compact propeller, and this uses a more typical piston inside of a dome, like we saw on the McCulley propellers. And so here there are no counterweights. So again, that blade, where the weight is distributed between the leading and trailing edge, the centrifugal force is going to try to get that blade to line up with kind of line up with that plane of rotation. And so it'll decrease the pitch. And when we want to increase pitch, when we want to slow the propeller down, the propeller governor is going to port oil up inside the dome to push on this piston. So again, they work opposite. Kind of a review of those blade angles. So here is a constant speed feathering propeller. Okay. So when we look at it from the side, the blades that are sticking up and down, or if we kind of look at it on the end, I guess, you can see the low pitch versus the high pitch. And then we go into feather, which is an extreme high pitch scenario. Okay, so some certain propellers have the ability to feather. Most of your single engines, there really is no need for this. We're starting to get into the territory of light twin aircraft. And light twins, we're talking about piston twins and smaller turboprop twins are going to be, they're going to be constant speed, they're going to have the low high angle, and then they're going to have the ability to feather as well. And so what feathering is for, the reason we have feathering is that when you have a multi-engine aircraft, okay, so something where there's two engines, two or more engines, typically two, you know, there are some three or four, excuse me, some four-engine aircraft out there now. But when we have a multi-engine aircraft, we want to have a way to, kind of got ahead of myself. We want to have a way to reduce drag if we have an engine failure. I'll go back to the previous slide in a second. So higher powered multi-engine aircraft, if you lose an engine and that propeller is at any angle besides feathered, so any angle where it's not perfectly forward, that air moving across the propeller is going to basically try to spin it. And that's going to create a significant amount of drag. If you have a propeller that's not in the feathered position, not only do you get drag from trying to push that sideways blade through the air, but the act of the spin that it induces increases that drag even more. So we want to reduce the prop spin. We want to stop it from spinning if at all possible. And we want to reduce the face of the blade that's facing into the wind just to reduce the drag from that as well. So there's a drag you get just from pushing the blade through the air sideways, as well as a drag that's induced by the spinning of the propeller. And so in a multi-engine aircraft, we want the prop to turn so the leading edge of the blade is facing straight forward as possible, so that air can easily pass over the blade and it's going to prevent it from spinning after that engine has shut down. So pilots need to be able to either identify that, or what is most common is pretty much anything that is a multi-engine aircraft that uses a constant speed feathering propeller, which almost any multi-engine aircraft is going to use a very, very few fixed pitch multi-engine aircraft. So it's going to have a system to feather it in order to do that. And most of these are automatic. So in flight, if we lose oil pressure, the propeller is somehow going to be driven to that low pitch position. Okay? And we'll look at how it does that. There's a couple ways it can do that. And so what we have here, some of those ways. So the counterweights that we saw, there will be a certain amount of spin, right? When the engine first shuts down, the engine's still spinning, or the propeller's still spinning in the case of a free power turboprop. And that air moving across the blades is going to cause it to windmill. You'll get the windmill effect. And so that creates that centrifugal force in the plane of rotation, where we can have a counterweight that's designed to drive the propeller to a feathered position. We also can have internal springs or internal air charge. So a lot of the propellers that we see, that we've studied, that you'll look at, that they use oil pressure to go to a fine pitch. It's an automatic fail-safe. So if oil is used to move that prop to a fine pitch position, then when that oil pressure is removed, when the engine shuts off and the oil pump's no longer running, and the oil pump inside the governor is no longer running because the engine's no longer turning the governor, that prop will automatically move to that feathered position. But we don't want that to always happen. Okay? During a normal shutdown, there are certain cases where having the propeller feather is a bad thing. Okay? And where that is when we look at piston and fixed shaft turboprop aircraft. So piston and fixed shaft turboprop aircraft, we don't want it to feather. Why don't we want those to feather? What's the problem with a feathered propeller after the engine shut down in something that's a fixed shaft or a fixed shaft turboprop or a piston engine? Yeah. Exactly. So it's going to create a lot of resistance if we try to spin that propeller. Remember, if we have our prop blades, I'm the propeller, right? It spins this way. And they're sitting in a feathered position like this. When we go to spin it, when we start to spin that prop, there's going to be a lot of resistance on it. And that's particularly important for piston and fixed shaft aircraft. Free power turbine turboprops, however, that's not typically the case. If you go look at the King Air, or King Air is a free power turbine, it goes to feather on shutdown. Why is that? Who in this room can explain to me the difference between a fixed shaft turboprop and a free power turbine turboprop? That's what I was afraid of. Okay, we're going to take a little side note and we're going to do an engines kind of. So to prevent feathering at shutdown, if you have a piston or a fixed shaft turboprop, there is going to be a set of pins that engage the blades when they slow down. Not slow enough, it still has enough oil pressure that it's being held in a fine pitch position. But now as the engine's slowing down, before the oil pressure drops off, the oil pressure is one of the last things to drop off. Because we want that engine, as it's turning, whether it's a piston engine or a turbine engine, we want that oil to be circulating anytime that engine is moving. So the oil pump's designed to create pressure, full pressure, even at lower RPMs. So as the engine's shutting down, it's still creating oil pressure. So the oil pressure is holding the blades in this fine pitch position. And when the propeller gets below, in this case, about 700 RPM typically, because you're talking about propellers that idle at like 900 to 1200 RPM. So as it gets to about 700 RPM, the oil pump is still working, and these pins will pop into place in order to keep it, as it slows down, the pins, centrifugal force holds them retracted. As it slows down, those pins will pop into place before the oil pressure is lost. In flight, what happens is there's a valve that can dump oil pressure. So if we lose oil pressure suddenly, if we lose engine power suddenly, these pins are prevented from engaging in flight, in a flight condition. And so in that case, it will auto feather. Because we do, if the engine shuts down unexpectedly without putting the levers into cutoff or without going to fuel cutoff on the mixture, if it just shuts down without that happening, then these pins are held in the retracted position, or they're not allowed to re-engage, and then the propeller will go to feather. But in a normal shutdown, when we put the engine, a turbine engine, into cutoff, or we put the mixture into cutoff on a piston engine, these pins will be allowed to go back into place and hopefully keep the propeller in a low pitch position so that it's easier for it to start. But if we have a free power turboprop, it really doesn't matter. So in that case, that system isn't even installed because it's extra complexity, extra weight. There's no reason to need it. And so every time the engine shuts down, it's allowed to go to feather. Okay. So the key, though, is auto feathering, propeller feathering. Pilots have to figure it out. And so if we don't want them to have to try to figure out which engine it is, what's going wrong, and react in a timely manner, you build these in such a way that they're going to feather automatically unless mechanisms are put in place which will keep them from feathering in the case of a proper shutdown. If they have any kind of a shutdown that's unexpected, they will go to auto feather. And so if you look at a cutaway, This is a propeller that's auto feathering, and we know that got it in the front. Governor oil is in the back of the piston, behind the piston to the left. And so when we use oil pressure, you can see that's going to push the piston to the right until it can hit the high pitch stop, right? But in the case of a failure, this air charge is able to drive that propeller to a extremely high pitch position, or essentially a feather position. And the low pitch position in this one is oil, and then the fact that the blades, this doesn't have counterweights on it. The blades want to go to that fine pitch position. They want to line up with the plane of rotation, okay, from the centrifugal force. Now, sometimes these systems on a fixed shaft turboprop or on a piston engine, occasionally they don't work as designed. For some reason, the propeller goes to a feather condition. Those pins fail to engage. And if the pins fail to engage, we got to have the ability to unfeather the propeller. And there's a couple ways we can do that. One is to start the engine. Piston engine aircraft, that's doable. It's not too bad. It's hard on the engine, but it's not the end of the world. Okay. A fixed shaft turboprop, like I drew originally, can actually cause an overtemp situation, because you cannot get the engine spinning fast enough with that blade and feather to be able to get the necessary airflow to cool the engine during the start process. And so on those, and even on piston engines where we don't want to have that resistance, we can have accumulators in the system. How many of you are familiar with an accumulator from hydraulics? You talked about that in systems yet? Maybe. What's an accumulator? What does an accumulator do? What can you liken it to? It can act as a shock absorber, but in this case, we're using it as something different. Yeah. Yeah, you're on the right track. So it acts as a pressurized fluid storage device. Okay, there's a few different ways to do it. When you're in systems, you'll get into the details of that, but typically it's either it has some kind of it's typically a nitrogen charge that creates an air spring, whether through a piston or through a bladder, where when the pump is on, the hydraulic pump, or in this case the oil pump in the engine that's acting like a hydraulic pump, when it's running, or the hydraulic pump, the oil pump that's in the governor, when it's running, fluid is forced into the accumulator under a certain pressure. And as fluid's forced into the accumulator, the nitrogen that's in there is compressed. It's squeezed, right, increasing its pressure. So it's going to try to, as long as that fluid's being held in by either pressure or a valve that's closed, you've got fluid under pressure that's held in this accumulator. But as soon as that valve opens, that nitrogen charge is going to try to push that fluid back out. So it's almost like a hydraulic battery, or it's almost like an oil-filled battery. It pushes the fluid back out after it's been shut off. And so we can have an accumulator that can provide a certain amount of oil pressure that can be used to drive a propeller to the fine pitch position. We can also have a crossover system, and that is, if we have a twin engine, we can start the engine that is not feathered. We can start the engine that's in fine pitch, and then it's able to supply a certain amount of pressure through a crossover system to the non-running engine in order to get that propeller blade, that set of propeller blades out of feather. Or there could be a dedicated oil pump. There could be a little electric pump on the engine that's able to provide oil pressure in that case, purely for it. So it's called an unfeathering pump. It doesn't run when the engine's running. It's just used in a situation where you need to be able to unfeather the propeller if for some reason it doesn't feather automatically in shutdown. So here's one example of an accumulator. This is there's a bladder inside of here, kind of a balloon filled with nitrogen. When the governor is running, it's going to send pressure, right, to control pitch. But it's also going to send pressure into this accumulator. And then there's a valve inside of the governor. So when the governor shuts down, it automatically closes that valve, storing fluid in this accumulator. And if we need to be able to bring the propeller out of that feathered position, you can see when it goes to feather, if we select the propeller to feather, there's that little arm can go there. But you can see this valve, except when feathering, it's open. So if it's not in that feather position and the engine shuts down, it will allow that fluid back out to push the blades to that unfeathered position. Okay. This diagram I showed earlier, where I was talking about the prop governor and then being able to port fluid up to the dome of the propeller, you can see here's another version of an accumulator that's shown here. So this one, instead of having a bladder, we've got an air charge separated by a piston that can move back and forth in this chamber. And so again, when the governor is running, when the engine's running and there's oil pressure, that oil goes up in here, pushes the piston up and compresses that nitrogen. So ultimately the nitrogen and the oil are at the same pressure. And if the engine shuts down and the propeller is not going to the feathered position, not going to the fine pitch position, the governor will allow fluid back out and port it to the propeller in such a manner that it will drive it to that fine pitch position. And by keeping it that fine pitch position, we don't have to worry about it, or it's a way to keep it out of feather so that the next time we start the engine, we are able to, it's in a finer pitch position. It's not feathered. In the same manner, I did mention crossover or oil pump system. You can replace this accumulator right here with either of those items. Okay. So in the case of a crossover system, this would be ported to the opposite engine, to a pressure line off the opposite engine, rather than to an accumulator. And so if you start the opposite engine, you're able to take oil pressure from one side to the other. Or an electric pump, you would have an electric pump in place of this accumulator. It would pull some oil from the sump in the engine. Same, run it through an electrically driven pump and be able to port that up through the governor and into the dome of the propeller in order to drive it to a fine pitch position for engine starting. Those are all backups. Typically, we want those pins, those centrifugal pins, to re-engage during a normal shutdown. But for one reason or another, they don't. Sometimes it's, if you're out testing, if you lose oil pressure, right? There are times you'll lose oil pressure if, when the plane's operating, they come into land, now we want to drive it back to be able to test the engine or figure out what happened, why it shut down. As maintenance technicians, we'll need to test these systems. We want to make sure that the auto feather system works. Right? It has to be checked every so often. It's an emergency system. We want to make sure that it works when required, because if it doesn't, the plane, in some cases, the plane can be nearly or totally unflyable. There's so much drag on one side compared to the other that all the plane wants to do is start to spin in a big circle. Anyone know what that can cause the plane to do? What? Bad things? What happens when a plane starts to make a real tight turn in a circle? What do you get? You get a spiral due to one wing stalling out. It'll actually cause the plane to have a tight enough turn that side that has the engine shut down, if it didn't feather, will be going slower than the outboard wing, the wing that's on the outside of the spiral. And it can actually cause that wing to stall and roll the plane over. It turns into a spin and then a roll. And so these are a system, we do test them regularly. Now, when you do test them, we go out, we do it on the ramp. You'll do it as students when you get to run the airplane. We don't want to run it very long in that feathered condition, especially if the engine's still running, if we haven't shut it down. It puts a lot of strain, a lot of stress on the engine. If it is a fixed shaft or a piston engine. Again, the turboprop, or the free power turboprop, like the King Air, we can take that out, we can put it in feather, and we can let it run in feather all day long if we want. It's not going to hurt it, because in that case, the gas generator is able to spin at whatever speed it needs to, at its idle speed, and it's not being dragged down by that propeller that's in a feather condition. So, okay. In fact, before we shut down, we put the prop in feather. If you don't, when you shut down, it just goes to feather. It's not the end of the world. Okay. The last kind of function we'll see with propellers is something that happens more on some larger aircraft. So the King Air has this. The Saab 340s I worked on have this. The Dash 8s, Q400 Dash 8s have it. Any kind of bigger turboprop, it's going to be a constant speed, feathering, and it's going to have the ability to reverse pitch. And it acts as a form of thrust reverse when we touch down, when the aircraft touches down. The crew is able to reverse or back the pitch of the propeller in such a manner that instead of pushing air back, instead of creating, it's going to push air forward. Now, it's not super efficient, because your trailing edge becomes your leading edge, and your leading edge becomes your trailing edge. But it's efficient enough that you can do it. Have you seen like the wheels up planes come in to land here, the blue and white turboprops? You ever hear the weird noise they make after they touch down? So if you're out here, you see one of those coming into land, or if you see the FAA's King Air coming into land, or if you see us taxiing the King Air, sometimes you'll hear this really loud buzzy noise after landing or as the plane's going and slowing down. And that's the propellers going into reverse. They go into what's called a beta range. So the beta range is essentially, so here on this picture, you can see we've got, the feathered position. This is our leading edge right here, trailing edge. I wish this was more leading edge, okay? And when we go to, a coarse pitch, it's something like this, leading edge, trailing edge, right? In this case, this propeller is spinning this way, coming out the bottom of the board to the top of the board. Takeoff fine pitch is like this. Those are all known as what's called the alpha range. Okay, the alpha range is our normal operating range when the airplane's operating. When we go into reverse, we go into something called beta range. And beta range begins at the point where this blade is perfectly fine, or where it's basically no longer has an angle of attack to the spin plane, to the plane of rotation. So that's 0 to then reverse. And so now you can see the plane, it's going this way, and sorry, I misspoke earlier. You still have your leading edge, but the face of the blade becomes the back, and the back of the blade becomes the face. Okay, so the aerodynamics are switched. Now you've got your curved side on the high pressure side, and you have your flat side of your blade on the low pressure side, rather than the curve being on, sorry. You have your curved face on the high pressure side, your flat face on the low. Rather than normally you have your curved face on the low pressure side and your flat face is on the high pressure side. And so anywhere from a 0-degree angle of attack in relation to the plane of rotation to negative is getting into the beta and reversing range. And as it turns, this blade's going this way, you can see now it's going to hit that air and scoop it forward, push it forward. Questions on that?